AP Chemistry, Hononegah High School. Today we'll be looking at sections 13.4 and 13.5. First, we'll look at ways of expressing concentrations. Now, one way you can express concentrations is qualitatively, using terms like dilute or concentrated. Dilute, relatively small amount. Concentrated, relatively large amount dissolved. The problem with that is it's not very descriptive, it's not very specific. So typically we prefer quantitative descriptions. And the five we're going to look at are mass percent, part per million and part per billion, mole fraction, molarity, and molality. Many of these you've seen in pre-AP. Now the first one, mass percent, like any percent, is really a part to whole situation. The part we're looking at is the mass of the solute dissolved in the solution compared to the total mass of the solution. So if you have something like a 4.0% NaCl solution, what that really means is you have 4 grams dissolved in 100 grams of solution. So fundamentally that would mean you have 4 grams of NaCl for every 96 grams of water. And that's something that you need to be able to understand, because we end up converting back and forth and moving from one type of concentration to another. So you need to understand that what this really means is that idea. So given a percent, you can assume you have 100 grams of solution, and you can actually look at how much solute and solvent you have in converting to other types of concentrations. Now, another name for percent by mass would be part per 100, because that's literally what it stands for, is how much in 100. Now, if we have parts per 100, it makes sense that you might also have parts per million and parts per billion, looking at how many particles would be in a million rather than 100. And if we have a very, very low concentration, we could use something like parts per billion to deal with it. And the whole reason we have parts per 100, parts per million, parts per billion is because it's an easier concept for people to understand compared to the more scientific concepts such as molarity and molality that we're going to end up looking at in mole fraction. Now, mole fraction, the next one, has the Greek symbol chi, and really it stands for the moles of A compared to the total moles of solution. Now, you have to be very careful. Typically, when we use mole fraction in this chapter, we're going to be using the mole fraction of the solvent most often. So you need to be very, very careful with mole fraction. Most concentrations, we think of it in terms of the part that's dissolving. In this case, we're looking at the part that is the solvent. And we're going to end up using that in a number of different calculations. Another idea to understand related to mole fraction is, remember, a mole fraction is a part per 1 calculation. So that would mean, since we have a 2-part system here, the mole fraction of the solute plus the mole fraction of the solvent would have to equal 1. So if you know the mole fraction of either the solute or the solvent, you can quickly calculate the mole fraction of the other. Next one is molarity, and this is one you're very familiar with from last year in pre-AP. It's typically our most dominant concentration in chemistry. You see molarities more than anything else. But one thing you do have to understand about molarity is, because it deals with the liters of solution, it deals with a volume. Volume is temperature dependent. So there are some sorts of calculations that involve changes in temperature that we really can't stay in units of molarity, because the molarity would actually be changing. So in those type of situations, what we're going to end up using is molality, which is moles of solute per kilogram of solvent. Remember, the idea here, and think about where you used this in pre-AP last year, we used it in situations where you're dealing with freezing point depression and boiling point elevation, where we were looking at change in temperature situations. Molality, because it does not include a volume in our part per whole or part per part comparison, is not temperature dependent. So there will be some applications that are temperature dependent that we end up having to use the unit for molality. Now, one of the things you need to fundamentally understand about these is how to convert back and forth from one to the other. And a common conversion that you end up doing is between molarity and molality. The key to that is understanding, if we know the density of the solution, we can use that as a conversion factor in our problems to allow us to convert back and forth between molarity and molality. And the book gives a really nice chart description of that idea for you to use. So keep in mind, make sure you take a close look at page 545 to look at how we use things like density to convert back and forth between molarity and molality. So it's not just calculating concentrations, it's using concentrations in problem and converting back and forth in concentrations for AP chemistry. Now the next section, 13.5, we're going to take just a brief look at today, and that deals with colligative properties. Now, a colligative property is really a type of property that depends only upon the number of solute particles present, not upon the identity of the particle. So any type of property that changes in this manner, it's independent of identity but dependent upon the number of particles, would be known as a colligative property. Now, some of these colligative properties you looked at last year, vapor pressure lowering, boiling point elevation, and melting point depression, those were all discussed in pre-AP. Osmotic pressure probably wasn't touched even in honors chemistry, but you did look at these two from a mathematical standpoint last year, and this one from a conceptual standpoint. But at the AP level, you really need to understand conceptually and mathematically how all these are related. Now, vapor pressure is the first one we're going to look at because it's really kind of the basics of what's happening with colligative properties. It's one of the easiest to see what's happening and why it's identity independent, and it also is the basis for several of the other calculations that we end up looking at. Now, because solute-solvent intermolecular force attraction, so because of those types of attractions that are existing, higher concentrations of non-volatile solutes that aren't dissolving, sodium chloride dissolve in water, it's going to stay dissolved in the water. Even at high temperatures, it's going to stay and the solvent would evaporate away. Really make it harder for the solvent particles to escape into the vapor phase. What they fundamentally do is get in the way. And the more particles you have in here, the more that they impede the evaporation process. So when you have a solvent alone, it's going to have an equilibrium vapor pressure. And as soon as you start to dissolve particles in it, those particles are going to impede the evaporation process, and evaporation rate is going to slow down. Therefore, your vapor pressure is going to go down. And that's why we call it vapor pressure lowering. Now, the vapor pressure of solution then is always going to be lower than the vapor pressure of the pure solvent. And the more dissolved particles we have, the more we're going to end up lowering the vapor pressure. And the calculation we would use to do that is known as Raoult's law. And Raoult's law, chi of A, is the mole fraction of the solvent A. This value right here, P naught A, would be the normal vapor pressure of A at any given temperature. And the key here is we're talking about the solvent. So remember, when you're calculating mole fraction here, you need to calculate the mole fraction of the solvent. And as soon as we start to dissolve particles into our solvent, the mole fraction of the solvent is going to start to drop, lowering the vapor pressure. The more that gets dissolved, the more you drop the mole fraction of the solvent, the more the vapor pressure is going to be lowered. And that finishes up our notes for today.